My today's session, and today I'm going to discuss about linear transformation. Linear transformation. Okay, so let's talk about this entity in my today's class. When we learn about sets, capital A and capital B, when we define sets in class, then after defining sets A and B, the next thing that we do, or in any mathematics book that you can get, that they define a function from the set capital A to set capital B. A function is defined where A is the set of it's called codomain and domain, and B is the set of set which is called range or codomain. Okay, so we define function on a particular set or from a particular set to another set. So we do this generally when we learn set. After that, we introduce function in the class. Similar is the case that is going to happen in today also. In my earlier classes, I discussed about vector spaces. We started with this notion of vector space, which is an algebraic structure. Now suppose we have two vector spaces, V and W. So V is a vector space, which I'm abbreviating as VS, and W is a vector space, which I'm abbreviating as VS. You can call it as VS, no, not VS1. VS1 seems to be the property. This is a vector space, this is a vector space. Now we have two vector spaces. Now suppose from this vector space, capital V, I'm going to define a function which I am denoting by capital T from the vector space V to the vector space W. I'm defining a kind of function from this vector space to that vector space. Okay. And this function is not just any function. It will, suppose it is going to satisfy two very important properties or characteristics. What are these? The function T is defined in such a manner so that, number one, if for, not if, let us not write it in this way. Suppose for all x comma y belonging to the vector space V, and C belonging to capital F. Now you see that there is one particular thing that before you define the function from the vector space V to vector space W, you have to take care of one important situation, which goes like this, that the two vector spaces under consideration should be defined on the same field. Okay, so you have two vector spaces V and W. So V must be defined on a field capital F. W should also be defined on the same field capital F. So therefore, say for example, if you think that you can define a function from the vector space R to R to C to, say for example, C, then you cannot do so. You cannot define such a function, because here the two fields R and C, they are different. Okay, so this is wrong. First of all, the first part that is very important in this particular case is to take two vector spaces into consideration which are defined on a same field capital F. From this particular field, we are taking the scalar quantity C, because you know that the elements of fields are actually called scalars, and elements of V are actually called vectors. You know this very well. So if I take two elements xy from V, any two elements xy from V, and any element C from the field on which the vector space V is defined, then we must have T of x plus y. Okay, this should be equal to Tx plus Ty. This is the first property that needs to be satisfied. The second property that is important is the following. For all X belongs to V and C belongs to F, for all X belongs to V and C belongs to F, if I apply the function T on the element Cx, that is TCx, this should be equal to C into Tx. If these two properties are satisfied, then we call the function, or rather in this particular case, we call it as transformation. Okay. We shall not use the term function over here. We shall rather use the term transformation. We call this transformation linear. And why it is called transformation? It's because it is transforming the vector Cx into another vector, which is Ctx. Remember this thing. Now here in this particular case, remember, it is also very important that X and Y belongs to V, X plus Y belongs to V because V is a vector space. But remember that Tx, this actually is an element of W, Ty is an element of W, and since W is also a vector space, so Tx plus Ty also belongs to W, since W is a vector space. And here, since V is a vector space, Cx belongs to V. Remember that Tcx will belong to W. Okay, and Tcx is same as C into Tx, so that is also an element of W. So remember this thing, which element belongs to which particular set, that is actually very important. So again, I am repeating, I started with two vector spaces V and W, which are defined over the same field capital F. This is the first criteria. We have defined a function capital T from the vector space V to vector space W. Now this function is not just any function, it is going to satisfy two important properties. First property is that if we select two elements X and Y from V, and if we choose an element C from F, where C is a scalar quantity and XY is a vector quantity, then if I add the two elements X plus Y, and if I apply the function on it, that is T of X plus Y gives you Tx plus Ty. And the second property, that for all X belongs to V and for all C belongs to F, if I apply the transformation on the vector Cx, it is similar to C into Tx. If these two properties are satisfied, the function, or rather the transformation, is said to be linear transformation. A very important property that you need to know is the following. We can call it as property 1. The property 1 says that suppose we had two vector spaces V and W, and since V is a vector space, so therefore it must have a zero vector inside it. V must have a zero vector, that is, which is called additive identity. We denote the zero vector by, say, 0 bar V. And W is a vector space which also contains the zero vector. Okay, the two zero vectors of the two vector spaces will not be the same because they are two different vector spaces, so their zero vectors will be different. So let us denote this zero vector by 0 bar W. Remember that if the transformation is linear, if T is linear, then T of 0 V bar, this should be equal to 0 bar W. That means if we have the vector space V and if we have the vector space W, and suppose here we have the 0 B bar, the 0 vector, and here we have the 0 W bar, that is 0 vector of W, the transformation T takes the 0 vector of the vector space of the domain set to the 0 vector of the codomain set. It transforms this 0 vector into that 0 vector. Remember, this is a very important property. Another property which is also very important is the following. Can I go to the next page? Can I go to the next page?
Sir,
Just a
wait,
minute.
sir.
Yes,
I'm
sir.
copying.
Okay, okay. Just once you are done, you just let me know. Have you understood what I have said so far?
Yes, sir.
Yes. Okay. Now,
Yes, sir.
whenever I will be starting solving the problem, I'll get to know whether you have indeed understood or not. So I'm just giving you the preliminary shots of the topic. Now I have not gone into the details of solving problems. That I'm coming gradually. Now, first of all, you need to know what is linear transformation. This is the definition. You just keep this definition in mind. And remember that if the transformation is linear, it takes zero vector of one vector space. It transforms the zero vector of one vector space into zero vector of another vector space. Okay. It can be easily proved. I'm not going into the proof of this because there are so many other problems which need to be discussed. This proof is a very trivial proof. Even since you are writing, I can show you the proof quickly. Now see, if here it is written, the condition given is that T is a linear. T is linear. If T is linear, that means T is satisfying these two properties. Okay, no problem. Now, if I want to find what will be the linear transformation of this zero vector, then you see that what we can do is the following. You can write this zero vector in the following manner: 0v bar plus 0v bar. And you see that T of 0v bar, this is equal to 0v, T of 0v bar plus T of 0v bar, because T is linear, and therefore T of x plus y is equal to Tx plus Ty. So it proves that T is a linear operator. I'm showing why T is linear. And T of 0v bar, that would be equal to 0 bar W, and T of 0v bar, that would be equal to 0 bar W, and the addition of this to 0 bar will be this. So T of 0v bar is equal to 0 W bar. Similarly, you can show the other property also. T of C into 0v bar, for some scalar C, you can easily show that this is equal to C into T of 0v bar. Try to show it later on. Try to elaborately, explicitly write it when you are free to do. I'm not going to write it over here. It will just kill the time. So this particular result is very trivial. So I'm not going into the details of that. Only remember that the zero vector of one vector space will be transformed to zero vector of another vector space. Okay, this is the first thing that I wanted to discuss. The second thing is that,
Sir,
yes,
can you just repeat the, just the statement of the property one once again?
statement of the property one means this one you are talking about.
No, sir, the one on the bottom that you have written property one.
Oh, property one means suppose you have R2. Okay, V is R2. What is the zero vector of R2? Can you tell me? Oh, R2 I'm writing. I'm writing R2 in this manner. This is not R2. R2 is this. What is the zero vector of this?
0, 0.
0, 0. Okay. What is, suppose I'm taking W is equal to M2 cross 2R. What is the zero vector of that?
Sir, 0, 0, 0, 0 matrix.
0, 0, 0, 0. Now, if I can find out a suitable linear transformation, say T1 from R2 to M2 cross 2R, if I can find out, I don't know what sort of transformation will it be, but if I can find out a suitable transformation which is linear from R2 to M2 cross 2R, it will be observed immediately that whenever we apply T on the zero vector of R2, the resultant will be the matrix, zero matrix, which is the zero vector of M2 cross 2R. This is the meaning of this particular property. Understood?
I mean, sir, this is the property of what? I mean, by
Property
proving
of
this, what
linear,
are we satisfying?
property of linear transformation. One of the
Okay,
properties
sir.
of linear transformation. It is, if we define any function, it is not going to take the zero vector of one vector space into zero vector of other vector space. If the transformation or the function is linear, then it can only take zero vector of one vector space, and it will give the image of this particular zero vector as the zero vector of the range or codomain. So this will become the image of this if capital T is linear. So it is the property of the linear transformation. Understood?
Yes, sir.
Okay, now let me show you an example, like a problem. Suppose I am defining a transformation like this. I have taken the set two vector spaces V and W as same. Here V is equal to R2 and W is also equal to R2. And suppose I am defining the transformation. I am defining the transformation as follows. T of A1 comma A2, because you know all the elements of R2 are ordered pairs. And it is written as, the image is written as 2A1 plus A2 comma A1. Suppose I am defining it in this manner. Define the transformation in this manner. And now suppose you want to check whether this particular transformation that I have written over here, it is the transformation formula that I have designed here in this particular case. We want to check whether it is linear or not. So question is whether it is linear transformation or something else. So let's talk about how to find it out. Okay, keep in mind that if T is linear, we have two properties. One property is T of x plus y is equal to Tx plus Ty. You have to keep these particular properties in mind. And the second property is T of Cx. This is equal to C into Tx. These are the two properties that we are going to use over here. And also you have to understood the elements, the meaning of the elements x and y from the context itself. Now here the context is R2. So you have to choose your elements x and y as element of R2, not just any x and y. So how to solve this particular thing? So first of all, let us choose, this is number one I'm showing. Let us choose x comma y, arbitrary x comma y from R2. These are the vectors. And you know that we know that it is already proved that R2 is a vector space. R2 is a vector space over R, where actually the field is R. This is from the first chapter, because in first chapter, in the first example, it is written as F and F is a vector space. Here F is taken as R and N is taken as 2. If I take F to be R and N to be 2, then we will find that R2R is a vector space, or R2 is a vector space over R. Okay. And we are selecting the scalar C from the set of real number, which is R. Okay, so from the field. So these are my choices. Now, since X belongs to R2, and here the context is the set which is a two-dimensional space. So therefore, then the form of X will be A1 comma A2, and Y belongs to R2. Since Y belongs to R2, then from this context, the form of Y will be B1 comma B2, because these are the elements of R2. We want to find out what is the form of T of X plus Y. So let's start. This is the left hand side. Okay. Now T of X plus Y means you are going to substitute the points, the form of X over here. So X is A1 comma A2.
A1 B1.
and this will be b1 comma b2, and this is nothing but equals to t of a1 plus b1. Okay, and this is a2 plus b2. Too many brackets are there, so you can remove the outside braces and you can simply write it as t of a1 plus b1 comma a2 plus b2. Okay, so this is the thing that we have obtained by calculating t of x plus y. Now let's talk about the RHS. Now in RHS we have tx plus ty. Now if I substitute once again the form of tx, we can write it as x is a1 comma a2. I'm not using too many brackets because these are confusing, and here I am writing ty as b1 comma b2. Okay, and this, t of a1 comma a2, by this transformation that I have written over here, the formula t of a1 comma a2 is given as 2a1 plus a2 and comma a1. This is the formula. By formula I am writing this, and similarly t of b1 comma b2 will be 2b1 plus b2 comma b1. Now you add the ordered pairs. If I add the ordered pairs, what will I get? The first two elements will add with one another. The first two elements will add with one another. So we'll get 2 of a1 plus a2 plus 2 of b1 plus b2 comma a1 plus b1. This is the outcome. And if you want to write it in some other acceptable form, you can take the two elements together, two common. You can write it as 2 into a1 plus b1 plus a2 plus b2, and this is a1 plus b1. So this is the outcome of tx plus ty. What will be the outcome of this? The outcome of this is similar. If I think this element to be, say, C1, and if I think this element to be C2, we can easily apply this particular rule to this formula. So it would be in terms of C1 and C2, this would be what? This would be 2C1 plus C2, and this would be C1 by the formula. Now you can resubstitute the form of C1 and C2 over here. Now what is C1? C1 is A1 plus B1. So let us put it T into A1 plus B1. And what is C2? C2 is A2 plus B2. So we get A2 plus B2. And what is C1? C1 is A1 plus B1 once again. And we get this. Now you just look at your LHS and you just look at your RHS. These two are same. So we get from this particular thing, we have obtained that t of x plus y is equal to tx plus ty. Okay, tx plus ty is equal to t of x plus y, which is the first part of the definition. That means we have proved the property, this particular first part of the definition over here. Understood? Have you understood the mathematics?
Sir, could
Yes,
you please repeat the C1, C2 part, sir?
C1, C2 means that since what is R2? R2 is the two-dimensional space. R2 means that is a two-dimensional space which contains all the two-dimensional coordinates. So in R2, the elements will be of the elements of R2 looks like this. It is an ordered set of ordered pairs A comma B, where A is a real number, B is a real number. This is the R2. This is the definition of R2. Now you see, just look at A1 plus B1 and A2 plus B2. These are numbers. A1, B1, A2, B2, these are real numbers. A1 plus B1 is also a number. A2 plus B2 is also a number. Now A1 plus B1, we can rename A1 plus B1 as C1 virtually in our mind, and we can rename A2 plus B2 as C2 virtually in our mind. Now if I try to look at this as simply T of C1 comma C2, now we can apply this definition. So T of C1 comma C2 would be what? Since T of A1 comma A2 is 2A1 plus A2 comma A1, T of C1 comma C2 will be 2C1 plus C2 comma C1. I'm just replacing A1 by C1 and A2 by C2. Now
Yes, sir,
again,
now I understand, sir.
now again I am resubstituting in place of C1, I am resubstituting A1 plus B1 and A2 plus B2. And we have got this form. My actual objective is to find out whether the form of T of x plus y and Tx plus Ty, they are same or not. But we have found that they are same. These two forms are same. These two forms are same actually. So therefore we can immediately say that T of x plus y is equal to Tx plus Ty. Now I'm going to the next part. Next part is number 2. Number 2 is this. We are going to show whether T of Cx is equal to C into Tx or not. Now let's start with the left hand side. Now C is my scalar, is a real number. It is any real number. So first of all, I'm going to find out the form of this T of Cx. In place of x, x is the member of R2. So in place of x, we can put its form A1 comma A2. Okay. So T of C into A1 comma A2, that I want to find out. And we know that in R2, the scalar multiplication is defined in the following manner. C of A comma B, C into A comma B is actually CA comma CB. From where have I written this? From first chapter. In first chapter, the scalar multiplication on R2 is defined in the following manner. So it is well defined. So we can apply this to in this particular case. So we can write it as T of CA1 comma CA2. Now you remember, you would see that your CA1 is a coordinate which is you can name as D1 and this as D2. And now you can apply the definition. Now you can please mute yourself. Please mute yourself. Whoever is Aditya Kumar. Okay, so CA1 is D1 and CA2 is D2. So we can apply the definition once again in terms of D1 and D2. So it is 2D1 plus D2 comma D1. And you can replace the form of D1 and D2 over here. So we get D1 is CA1 and D2 is CA2 and D1 is CA1. So it's just a matter of renaming the things. So we can write it as 2CA1 plus CA2 comma CA1 like this. Okay. Now you see that we can take C common from here. So we can write it as C of 2A1 plus A2 and this is A1. And if I look at this 2A1 plus A2 comma A1, this form, this is nothing but your C, this is nothing but your T of A1 comma A2. Just from the definition I'm writing. This I'm writing from the definition. Okay. And therefore we directly see that we started with LHS and we have directly obtained RHS. Okay, we don't have to show it separately. It is directly coming. So we observed in the previous stage, we observed in this part 1 that T of x plus y equal to Tx plus Ty. And now we are observing that from this we are observing that T of Cx is equal to C into Tx. And therefore from the two properties from 1 and 2, we can say that the transformation TA1 comma A2, which is 2A1 plus A2 comma A1, this transformation is a linear transformation. And it is proved. And the result is proved. Have you understood?
And sir, if the transformation is from one vector space to a different vector space, then we also need to prove that zero vector property.
No, you don't have to prove. This is the definition. You just need to show the definition. These two things you need to prove. Number one and number two. Zero vector is, we don't have to talk anything about the zero vector. Okay, so you just have to show that with whether property one and property two are satisfied or not. That would be all right. To show whether the transformation is linear or not. We don't have to talk about the zero vector, but you can simplify the thing a little bit further. The simplification is in the following manner. There is one theorem which goes like this. So I'm writing the theorem over here. So instead of showing these two properties 1 and 2 separately, we can show the following thing also. It is said in the theorem that T is linear. Any transformation from V to W is T. This T is linear if and only if. That means it is both way true. T of Cx plus y, T of Cx plus y, this would be equal to C into Tx plus Ty. Okay, for all xy belongs to V and C belongs to F. So we have to, we can also take the help of this particular theorem and we can directly show. If you are not, if you are finding this is too, I mean, in detailed, don't have to put it in a detailed version. So you can directly consider this to be the left hand side and that to be the right hand side. You can start putting the things on the left hand side and using the properties of the vector addition and scalar multiplication on the vector space under context on left hand side and on the right hand side, and you can show that both the forms that will be obtaining, they are same. So you can take the help of these two, or you can separately show the property 1 to be 2 and property 2 to be 2. So whatever way you can do it, if these are satisfied, then we'll say that the thing is a linear transformation. Let's talk about another example. Example 2. Suppose I'm defining a transformation in the following manner. Suppose define T colon R2 to R2. I'm defining a transformation as by T of A1 comma A2 is equal to A1 minus A2. Okay, so this is the transformation. Now, question is it linear? Is it linear? Is it linear transformation? What do you say? What is the geometry
so that
of
is
this?
A1 minus A2.
A1 minus A2. What is the geometry of this? The geometry goes like this. Suppose I'm showing you the geometry of this particular thing that I have trying to show over here. Okay. So I'm drawing two axes because R2, since I'm considering R2, it is a two-dimensional plane, you know. And suppose I'm choosing the coordinate A1, A2 over
So
here.
mirror image.
Huh?
Reflection about
Yeah.
the x-axis.
Reflection about the x-axis. Yes, exactly. So we are getting the thing like this. You can already see it in the book, but in the book, on the result is shown, but how to prove that it is linear, it is not mentioned. So you have to check it out. This is not a drawback actually. Actually, the book wants you to do the problems by yourself. So they are not showing you the details, every details of the calculation. But you can easily identify because I have already shared the book with you. So you can easily see from the book that this is nothing but the reflection about x-axis. If I consider a similar thing, which is not mentioned in the book, say for example, if I give you another transformation, which I name it as T1, which is A1 comma A2, and I'm writing it as minus A1 comma A2. You can also, what is this? This is reflection about y-axis. You can also check. Yeah, you can also check whether this is linear or not. So say for example, this thing. So you can try to show whether reflection about x-axis is linear or not. Now it is in the book, it is said that it is linear, but I want all of you to verify it by yourself. Reflection about x-axis whether this is a linear transformation or not. And these particular things, these particular three transformations are there. One is reflection about x-axis, another is rotation, and another is projection, as you can see from the book. These are very useful in quantum computation and machine learning. So machine learning is specifically based upon geometry, you know, so, and quantum computation also. So therefore these things are actually very much required over there. I'll not be able to show you tell you the details of that right now, but it is required that you have to believe me. Your job is to check whether this transformation is indeed linear or not. And now suppose we have this proper theorem, so we can take the help of the theorem and we can check whether this is linear or not. So let's try to apply the theorem over here. Now, if I take the theorem, take the help of the theorem, so we can start with the left hand side. Before that, we must select two elements x, y from R2, and we can select an element C from R, the field. And in this session is actually running out. So in the next session, we are going to put your attendance. Okay, I'm not taking attendance in this particular session. So you start with this left hand side. So you start with T of Cx plus y and put here C into A1 comma A2 plus y, you can consider it as B1 comma B2. Okay, apply the scalar multiplication rule. It is CA1 comma CA2, and this is B1 comma B2, and then you proceed and try to show whether the left hand side is coming or not. That is C into Tx plus Ty dot 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 dot. This you can try to do by yourself, and let's meet in the next session.